So at the end of last lecture, I had stated this theorem, myself, Hacking and Keel, which constructed this. So we have xi, spec of this ring of regular functions on this punctured, or this deformation of the vertex minus the origin. This is a plaster spec AI. This is a flat deformation of the invariants. And the key point that you have to prove in order to prove flatness, I mean, this is just some scheme a priori. The key point is to show surjectivity of the sorry, that might be hard to read there. Let me rewrite that. Okay, so this is just restriction of, maybe I should write it like that. Restriction of functions to the fiber, the reduced fiber of this map. And we know what this is, right? So this is just the ring of regular functions. It's the same as the ring of regular functions on Vn, because the Vn is an S2 scheme, so any function defined on the complement of the origin extends across the origin. So this is the same thing as functions on Vn. And that's essentially what S2 means, is that functions extend across codimension to subarrays. So we need to be able to take any function here, and which is something we understand very well. Vn is something very simple, and in particular is just generated by monomials. So gamma Vn over Vn has basis consisting of things in the form x to the I with a, x to the I minus I plus 1 to b, I ranging between 1 and n, and a, b, b natural numbers. And of course, these monomials are in one-to-one correspondence with integral points of our affine manifold B. So this set is in one-to-one correspondence with B of z. And so here we're thinking of, so here's B. Each of these cells is isomorphic, linearly isomorphic to the first quadrant in R2, and that has some integral points in there of those points with integer coordinates. So if this, say, this represents x1, this represents x2, then something like this would represent x1, x2 squared, and so on. So the integral points are sort of clearly in one-to-one correspondence with this generating set for this basis of the ring of regular functions on Vn. And so the whole point is that we have a mechanism for taking a monomial of that sort, which lives down here, and lifting it to a function here. And those are the theta functions. And so I think Bernd has already, yesterday, I guess Bernd has left already. Yeah, so So corresponding to a point P in B of Z, that's a set of integral points of B, we have a theta function. Theta B, and this will be a section of a regular function xi function. Okay, so I'll just sort of quickly sketch, because I'm not sure exactly what Bernd said. I'll just say a few words about that. So we have B, and we have some scattering diagram sitting here. And we have a point P in B of Z. And then we also choose some base point Q at any point in B. And you should think of it as being inside some chamber, hence representing some chart for the this scheme xi circ. We had built up this, remember we built this up by gluing some standard pieces, and if you select a point somewhere, it selects out one of those standard pieces. So if you put the point in here, it will be some copy of the algebraic torus, thickened algebraic torus. If you put the point here, it would be that slightly more complicated scheme. I don't want to go through very technical details for this. And then the point is that we have these broken lines ending at Q with asymptotic direction given by P. So you would have, for example, let's see, that's the asymptotic direction. So you would have, for example, a line going parallel to this direction, ending at Q as an example of a broken line. Or it's possible that these broken lines can bend at one of the rays in the scattering diagram. And so what happens is initially you have attached to each of these incoming edges, you have the monomial corresponding to P. That would be some uniform xi, something like this. And then as it moves along, if you cross a wall, you apply the wall crossing automorphism to it, and you take a new term in that expression, and that gives you a new direction. You head towards Q. And we want to sum over all the final monomials. Theta P is defined to be a sum. So at the point Q, in the chart given by Q, is defined to be a sum of monomials. I write a sum over gamma of mono of gamma, where mono of gamma is the final monomial on gamma. So it's the monomial attached to the final line segment. So I hope that Bernd had gone through this in a bit more detail. He told me he would, so I will leave it like this. He did. Good, okay. Okay, so let's go back to the example of the del Pesto surface. Now, I skipped ahead in last lecture to tell you what the scattering diagram is. There are five rays, something like this. And let me, let me shade the part that's actually there. And then remember, let's see, 1, 2, 3, 4, 5. Maybe I should draw this. 6. This ray is attached to this. So you cut out this wedge and then boom. Okay, and then we have 5 rays in the scattering diagram. looks something like that, and the attached functions are 1 plus z to the e1 x1 inverse, 1 plus z to the e2 x2 inverse, and so on. So this would be 1 plus z to the e5 x5 inverse. Those are the attached functions I showed you last time. This comes from just the exceptional curve and its multiple cover contributions. Okay, so then you can associate, let's take the initial generators. Of each of these 5 rays. By the way, let me go back to this construction, this construction for a second. Here's a much lower tech way of thinking about taking the spectrum of this ring. If we know that we have functions, here we have functions theta I is equal to theta pi. That's 5 functions on this scheme. So we can use those 5 functions to map that scheme into the affine 5 space over spec AI. Now, we're missing a point, we're missing the origin, and you just take the closure of that scheme inside affine 5 space. And that's really what this procedure is doing. So it's just giving us a way of embedding into some affine space in such a way that when we take the closure, we get the missing point. Okay, so we have these 5 functions, and then it's not too hard to see. And so this will be an exercise in understanding the definition of broken lines. And I don't want to do it because I think that Bernd probably already did something very close to this example. But you can check. So exercise. These theta functions satisfy an equation. And I'm going to actually show this in a different way somewhat later. So these functions satisfy the equation theta I minus 1 times theta I plus 1 is equal to z to the class of di times theta I plus z to the class of di. So the way, given what I've told you so far, the way that you would do this exercise is you would just choose some base point, q, and expand the theta functions at that point, multiply things out, and then try to guess what expression that is in terms of some theta functions. But let me show you that there's a very simple product rule which will actually tell us how to do this. Okay, so in general, given P and Q in B of Z, we want to understand what the product theta P times theta Q is. So given that these theta functions actually generate the coordinate ring as a vector space, or as an AI module, we should be able to write this as a summation for alpha p over r in B of z of alpha pqr times theta r. So here these things are just some structure constants for the algebra structure, and alpha pqr had better lie in the ground ring A sub r. Okay, so that's not saying anything at all. Any product rule can be written like that. So let's understand what the coefficients alpha, p, q, r are. So here's the important part where alpha, p, q, r can be written as a sum. I'll explain the notation in a second. Gamma p, gamma q, c gamma p, c gamma q, where we sum over all broken lines gamma p, gamma q, with asymptotic directions P and Q respectively, and base point R, so we end at the point R, and let's write R. So since I've been trying to keep things relatively explicit, let me write R in terms of coordinates. So R is sitting inside some cone. So R is sitting inside some sigma I plus 1, which I identify with the first quadrant. And let me write R as equal to A and B. And then the final monomial, so we have mono of gamma p, will be some c gamma p, that will be just living in A sub I, times xi to the, say, AP xi plus 1 to the BP. So this is what the final monomial will look like on gamma p. And c gamma p in this expression is just the coefficient of that final monomial. Monomial of gamma q is c gamma q xi to the aq xi plus 1 to the bq. And then finally, and this is really the important thing, there's a balancing condition. Let me write it here. With R, so AB should be equal to AP plus BP, sorry, AQ, BP plus B. So what does this mean pictorially? So again, we have this example of scattering diagram. Here's B. We have these extra rays in the scattering diagram. And then we have points P, Q, and maybe R. And we want to look at broken lines, which have asymptotic directions P and Q. So for example, we might have something like that. Maybe it doesn't bend at all. Then we might have something like that. And remember, in the definition of broken line, these exponents here tell you the direction. So this direction here is the tangent vector AP, BP, and this direction here is the tangent vector AQ, BQ. So these two vectors have to add up to the vector given by R. And I like to think of it, I actually like to draw this, instead of having the arrows going this way, since I like to think of the broken lines coming in, so I'll just modify this picture a bit. I think of these coming in, and then the two final velocity vectors here add up to a vector which is just minus R, so pointing towards the origin. So from the point of view of tropical geometry, this looks like a little balanced tropical curve here, although this is really just an arrow, it's not a line segment, so it doesn't continue. So what we're doing is we're summing over all diagrams like this. Think of this as a little trivalent version of a broken line. It has two broken lines joining up, then a little bit of output. We're summing over all pictures like this, and we're multiplying the coefficients, and that gives us the tropical product rule. Now, it turns out this is really easy to actually show, and I'll show it for you right now. So let's just expand theta p and theta q at the point R, at the base point R. Okay, so what that means is that we're just writing theta p as some gamma p of monomial gamma p, and theta q as sum over gamma q, monomial of gamma q, where gamma p and gamma q run over all broken lines with asymptotic directions p and q, and with endpoint R. Okay, so that's just the definition of the theta function in the chart near R. Okay, so when you multiply these together, of course you just use the distributive law, you get lots of things that form mono of gamma p times mono of gamma q, and a priori this is a huge mess. So the question is, how do you read off the coefficient of theta R there? Well, let's look at the coefficient in that expression of the monomial corresponding to R. So let's look at the coefficient of xi to the a, xi plus 1 to the b, that's the coordinates for R, in the expanded product. Summation gamma p, gamma q, mono gamma p times mono of gamma q. Now, first of all, there are a couple of points here. The first thing is that that coefficient is exactly what I've written down over here. And why is that? Well, when you multiply these things together, if you want to get an xi to the a, xi plus 1 to the b, you need precisely this condition. That's the balancing condition. So this expression over here is clearly the coefficient of this, of xi, of this monomial in this expression. So the formula given for alpha PQR is the coefficient of xi to the a, xi plus 1 to the b. So that's the first thing. That's where this expression comes from. But now the next question is, well, why is that the coefficient of theta r in the expression? Right? I'm not claiming that alpha PQR is the coefficient of xi to the a, xi plus 1 to the b. Okay. Yeah. Can you hear me now? Good. Okay. Yeah, I was expecting that to happen. Okay, so I don't quite know where I faded out, but right. So the point is, this is what we're claiming is the coefficient of theta r. It's clear it's the coefficient of this monomial in the expansion. So how do we compare the two? Well, let's think about how can this monomial, so this, this product is supposed to be a sum of theta functions. Let's think a bit about how this monomial would appear in one of the theta functions. So the claim if xi to the a, xi plus 1 to the b appears in some theta s expanded at r, then s is equal to r, and the monomial has coefficient 1. So the only way this monomial can show up in this product is, or in the product, sorry, just erase it, the expansion in terms of the theta r's, the only way it can show up is from theta r itself, and since it's coefficient 1, that tells you the coefficient of theta r in expansion is the same as the coefficient of this in this expansion. Okay, but that's very easy. This is proof by picture. Same picture here, but I'll redraw it. All right, so we have R here, and that's the endpoint. And so now we have some broken line that gives this monomial. Now, the point is that this direction here, this is AB, right? R is equal to AB. And according to rules of broken lines, if the final monomial is x to the xi to the a, xi plus 1 to the b, then it has to come in that direction. So it has to come in from direction AB, which notice is straight out from the origin. Now, that means that it will never hit a ray of the scattering diagram. It's just going to go straight out. Right, so it has to go straight out to infinity, and that's a broken line for R, and it's a trivial broken line. It never bends and never requires a coefficient. So we have one broken line. It's the only possible broken line. And has asymptotic direction R.
So
yeah, we have a question here. Yeah.
Last time when we talked about A and B, we say that's the primitive direction. So all the R are primitive?
No. Okay. So the question is, last time when I was using the notation AB, I was assuming A and B were relatively prime. That was primitive. Here it's arbitrary. It does not need to have. It need not be primitive. There's any. You might have any point contributing to the product. Okay. So that's the proof of the product rule. Very simple. And so now you can, so that exercise I gave you a bit earlier to check the product rule for the theta functions for the del Pesto surface is now relatively easy, and I'll again leave it to you to check. But I mean, let me just draw one more picture. is the incarnation of something sort of very stupid if we're just think of the coordinate ring of an algebraic torus. So suppose we just have the ring, say, k bracket x1 plus or minus 1, x2 plus or minus 1. And we want to describe multiplication of monomials in here. Well, if you have two monomials, let's say here's the origin. So I'm going to draw just a lattice. So this is the group ring of the lattice. Suppose you want to multiply two monomials, say this monomial and this monomial. Of course, that's when you multiply these two, if this is the origin, you just get that monomial. But another way of thinking about that is that you can draw a little picture. You can draw this picture where you have a ray going out to infinity this way, a ray going out to infinity this way, and these precisely balance in the sense that this is, of course, direction 0, 1. This is direction, so what was going out that way? That's 1 minus 1. The sum is 1, 0. Okay, so this stupid little picture, well, maybe, I mean, multiplication of this ring is very easy. This picture is exactly the same picture we're drawing over there, and this is a generalization of that picture, where now these lines need not be straight, but they can bend. Okay, so that's the product rule, and now you could do the exercise directly without expanding the theta functions themselves. You just have to look at each possible point in B and R in D and see whether you can draw two balanced tropical lines ending at that point. Okay, so now this leads us on to the final subject of my talks, which is this is now a tropical description of the product rule. So that gives us the algebra structure on the ring we're trying to construct. On the other hand, when you have some tropical object, the general philosophy is that tropical objects should reflect some kind of genuine polymorphic or maybe logarithmic objects. So maybe we can go directly. We can skip all this stuff that we've been doing up until now, well, other than log geometry. We can skip scattering diagrams. We just go directly and write down the ring structure. And we're going to do that by reinterpreting these tropical pictures as a type of logarithmic or Witten invariant. So this brings us now to general mirror symmetry construction. So this is work in progress by myself and Bernd. There's an announcement paper dating from sometime last year on the archive called Intrinsic Mirror Symmetry, and the full argument is almost written up, but for various reasons it will probably take a while before it finally is on the archive. So what we're going to do is we're going to start with a log smooth pair xd. So we put the divisor log structure given by d on x, and this will make it log smooth over spec k, over just the ordinary point. So for example, if you don't want to be too fancy, d could just be normal crosses. Now, what I would like to do is associate directly a ring to this pair, and in some sense, what this ring is going to be a piece of an analog of quantum cohomology for the relative setting. So, unfortunately, we haven't defined the full ring yet. That's another project, but we can do enough in the case that well, okay, so what is D? So we'll be able to define a ring in cases where either KX plus D plus or minus KX plus D is Neff. So either KX plus D is Neff or anti-Neff, or XD is log Calabi-Yau, and that means i.e. X minus D carries a nowhere vanishing top dimensional holomorphic form. With at worst simple poles along D. Okay, so that of course includes the case that Kx plus D is 0, so there's a certain overlap between these two cases. But this case allows some sort of non-minimality, and in particular this implies that Kx plus D is some summation of boundary divisors. So if I write D as summation di, these divisors always should be viewed as reduced by the reduced divisors. But Kx plus D will be some summation of boundary divisors with the AIs greater or equal to 0. That's what the simple poles. Well, the fact that it's nowhere vanishing in the interior says Kx plus D is at most is supported on D. The fact that it has a more simple poles tells us that the AIs are greater or equal to 0. So the genuine minimal log Calabi-Yau case would have all the AIs being 0. Now, I'm going to not deal with this case. This case is slightly more complicated, not much more. You can read about it in the paper. But it is an important case because this allows us to not worry about whether we have a minimal model for our pair. And of course, in all dimensions, we don't necessarily know if minimal models exist, so that's good. If you have log Calabi-Yau, if you have X minus D, you just find some normal crossings compactification, and then you can apply this procedure. Okay, so I'll stick to this, this first case. Okay. So we've done a lot of the notation already, so we'll let B be the tropicalization of X as before. The reason why this case is a little bit different is just because you don't take B to be the tropicalization of X. You throw out those cones that involve divisors with AI greater than 0. That's the only real difference. Now, unlike before, we're not going to worry about an affine structure. If XD is genuinely sort of minimal log Calabi-Yau, so Kx plus D is 0, then there is a way of putting an affine structure with singularities on it, which is also in that paper, but we won't need it. And then we have B of Z, a set of integral points on B. also fix some data. We'll take P contained in H2 of Xn, a toric monoid as before, containing all classes of effective curves on X. Okay, so far this should look exactly the same as what I did yesterday in the two-dimensional case. And then we'll choose I contained in K bracket P, monomial ideal, with AI being K bracket P mod I as before Artinian. So that's going to give us the base of we're going to build an algebra over that ring. Okay, so far it's exactly like yesterday. And now our goal define an AI algebra structure on the ring, on the AI module, the free AI module, which is just given by, I'll call this Ri, is the direct sum of all integral points of V of AI. So just as a free module generated by the integral points of B, and I'll call it the generator corresponding to P, theta P. Right? Because ultimately, if one did this in the surface case, this would coincide with the theta P's, which we define using broken lines. But here, there's no broken lines, there's no scattering diagram, it's just a symbol. Okay, so how are we going to do that? Well, again, we just write out structure constants. So theta P times theta Q should be sum over all R, B of Z, alpha PQR, theta R, where alpha PQR is in the ring AI. Okay, so I'm not saying anything yet. We haven't defined those constants. And then I have to tell you something about those structure constants. So the next thing you can do is you can write, is alpha PQR is in this quotient of the monoid ring. I can write this as a sum over all beta in P, but not in the ideal I. And now I'll write this n beta PQR Z to the beta. Okay, so I'm still not doing anything. All I'm doing is I'm saying, well, I have a polynomial, I'm writing it out, and they're the coefficients of the polynomial. Okay, so now the question is, what are these things? So these should be in our ground field K. And in fact, I'll actually be in the rational numbers. I'm assuming we're in pairs. Well, we've always been in pairs to 0, so these will actually be rational numbers. So this whole construction works over the rationals. And now I'm going to define these numbers. And that's going to be the real punchline of the construction. So, definition of the n beta PQR. Okay, so first a little bit of notation. So for R in B of Z, there's some minimal cone of B. There's a minimal cone of sigma of x. I'm writing sigma of x here instead of B because sigma of x you should think of as including the information of the polygonal cones. There's a minimal cone of sigma of x containing R. And this cone corresponds to a stratum of x. Which I write as ZR. Okay, so here there's a order, by stratum of x, I mean one of the, well, x itself, one of the divisors, intersections of divisors, and so on. So you have a picture here, we do the two-dimensional case. If R is the origin, that corresponds to, that's the zero cone, that corresponds to all of x. If the point is on a ray, that corresponds to a single divisor, and ZR is that divisor, and if the point is in the interior of the cone, that cone, two-dimensional cone, that cone corresponds to one of the double points of D. Okay, so this is just selecting out some intersection of divisors in D. Okay, so now let's also pick a point Z in ZR general. Well, it doesn't have to be general, Gross-Hacking-Keel theory takes care of that. And now I can tell you what the numbers n beta PQ are. So n beta PQR are the number of three-pointed genus zero curves of class beta, so they represent the homology class beta, with contact order so remember, let me say, I think I said this yesterday, but I'll say this again. Right, so these cones in the tropicalization correspond to duals of the monoids of the Gauss sheaf of X. And contact orders are elements of the duals of the monoids, so selecting a point in here is the same as selecting a contact order. Saying, for example, this point here is the same, we have a contact order with this divisor given by, you know, the order of the tangency should be whatever multiple of the primitive generator this point is. If we have a contact order here, it says we're tangent to both this and this to certain orders. Okay, so we're going to have contact orders P, Q, and now here's the mysterious thing, minus R at the 3 points. Now at this point you should definitely be a bit unhappy, because what does minus R mean? It means that you're going to have negative orders of tangency. So I'm going to have to come back to this point, which is a very important point. So we have contact orders P, Q, and minus R at the 3 points, and the point with contact order minus R maps to this chosen point, Z. Okay, so I think of this point, I mean, maybe I should draw one of our trees again. So tropically what's going to happen is that these things will correspond to some kind of curves where the output, the inputs, so the inputs here are coming in the direct asymptotic directions P and Q, and then there's one extra output point which has this mysterious contact order of minus R at the point Z. and that will represent this arrow pointing inwards towards the origin. Right, so when you have these unbounded rays, of course, corresponding to contact orders, those are always sort of positive tangency. Here we have some weird negative tangency. Okay, so we need some kind of theory which will generalize logarithmic invariants, which will allow us to talk about negative orders of tangency. Okay, so fortunately, it's only a slight variation of what we've done before. It's not a deep new theory, but it's a modification of the logarithmic Gross-Hacking-Keel theory we've already seen. So this is something being, so negative order of tangency is incorporating something which we're calling punctured invariance. And this is currently being developed jointly with Gromovich and Chile Chen. You can find on my website a draft of the paper fully defining these things. It's extremely drafty, and the other half of the collaboration is now completely rewriting it, so it might be a while before it gets released as an official preprint, and the definitions might look a bit different by the time the book releases. So it's very much in flux, but this should be, what's there should be entirely correct. So the idea is that, remember when we were talking about the classification of log smooth curves, we had mark points came in intrinsically into the picture. And we also had nodes. Nodes aren't that interesting. But what we're going to do is introduce a new type of special point called a punctured point. And these points have slightly bigger log structure than mark points, which will allow us to encode negative orders of tangents. So let's suppose we're given a log smooth family of curves. Along with a section P, you should think of this as a section, as a morphism of the underlying schemes, because there's no log morphism. Well, actually, there is. Yeah, no. Along with a section, which is disjoint from all special points. So it shouldn't intersect another marked point, and it shouldn't go through a node. Okay, so now suppose you want to say, well, we actually really wanted this point P in the curve to be marked. How would we do that? Well, to mark point P, we use the log structure. So what I'd like to say is we just take the original log structure on C, and we take the direct sum, leave a bit of space here, we take the direct sum with the divisorial log structure coming from P, or if you will, the image of P. Right, so this is a nice little log structure on C, which just has an N ghost sheaf along the point P, and this is the old log structure. And then we clearly have a map, structure map to OC, given by S1 and S2 just goes to the product of the images under the two structure maps, the one for MC and the one for this. The one structure map for this, of course, is just inclusion of the functions. Okay, well, the only trouble is, of course, the inverse image of OC star is way too big because there are two copies of OC star here. So what you do is you identify them by taking fibered sum over OC star. So you just, if you have something in here, which is, what you're doing is you're identifying invertible function times S1, S2. Let me write this down. Invertible function times S1, S2 is equal to, in this fibered sum, to S1 by S2. And now, in particular, you only have one copy of the invertible functions sitting inside this sheaf, and then this becomes a log structure. So this is just one way of describing what a mark point is on the log structure. Okay, so now I'm going to modify this a little bit. So this is a mark point. To puncture the point, consider a subsheet, I'll call it E, of almost the same thing, MC direct sum over OC star, but now, instead of taking MCP, I take its group. So what does this group mean? Here, group, if you have a monoid P group is the Gross-Hacking-Keel group of P. This is just it's just the set consisting of symbols P minus Q for P and Q elements of P, modulo an obvious equivalence. So P minus Q is equivalent to P prime minus Q prime if P plus Q prime equal to P prime plus Q, just the obvious rule. So that's the Gross-Hacking-Keel group of a monoid. So what's going on here, if you compare it with what we have over here, this thing is just regular functions on C which are invertible outside of P. So, for example, T is a local parameter, it contains powers of T. Taking the group just says we're adding the inverse to T. We're adding T inverse, that's it. Now, that immediately causes problems because if you try to define a structure now, I suppose you had, say, 1 in here and T inverse here, that maps to an element that's not an OC. It maps to T inverse under this. So what we do is we take essentially the largest possible subsheaf on which the structure map could make sense. So here E is defined, so be slightly careless about this. Is of course a sheaf, not a set, but on a this can be defined stalkwise. And the condition is that S2 should lie in the actual sheaf here, not the group, if alpha of S1 is not 0. the point is you can then define a structure map from E to OC by alpha of S1, S2 is equal to, well, alpha of S1 times alpha of S2 if alpha of S1 is non-zero, and if it is zero, well, there's an obvious answer is to take that to be zero. Right? We have to do it as a case in two cases, because alpha of S2 doesn't make sense if S2 is some line T inverse as a pole. So what we're doing is we're allowing functions with poles at the point P, but only as long as they're counterbalanced with a piece of the log structure MC. So if, for example, C had the trivial log structure, so MC was just OC star, you wouldn't get anything new. It would still just be a marked point because this condition always holds. Right? If alpha on OC stars is an inclusion, so that will never be zero. So example. If MC is equal to OC star, then E is just MCP, and all we've done is we've marked the point. So we don't get anything new. But if, say, C is a smooth curve, of course, in order for this to happen, C would also have to be a smooth curve. C is a smooth curve, and MC, let's say, OC star plus N, but that's really just the pullback log structure from the standard log point. This has the standard map alpha of Sn is equal to S of n is 0, and 0 of n is not equal to 0. Okay, so in this case, as long as S1, if the second coordinate of S1 is 1 or larger, isn't 0, then alpha applied to is 0. And then we allow ourselves to have any element of MCP group. So here, let's look at E bar, the Gauss-sheaf E bar, at the point P. Okay, so this is contained inside the stock of the Gauss-sheaf of C at P plus the stock of the Gauss-sheaf of CP of the divisorial log structure at P. But the group of that is, remember, we're allowing inverses. So this is equal to n plus z. And then it's easy to see from this definition that E bar P is equal to the set of pairs A, B, with B in N if A is equal to 0. Right, so if A is equal to 0, that means, well, that's A's N here, that means that SA maps to something non-zero, and then by the definition of E, that forces the S2 to lie in the ordinary divisorial log structure. Okay, so that's a weird monoid. Let me just draw that monoid. So here's the monoid. So first of all, what it's saying is if the first coordinate is 0, we're only allowed elements of the natural numbers for the second coordinate. But if the first coordinate is non-zero, we're allowed any integer for the second coordinate. So this is not a finely generated monoid. It's a bit ugly. This is one of the things we're arguing about whether, so no matter how you formulate the theory, there's some ugliness somewhere. And as all of us co-authors are arguing with each other as to where we want to put the ugliness. This is the way I did it. It doesn't have to be done this way. There are other places to put the ugliness. And one of the things that means is that you can't appeal to all of the literature that was doing things for fine saturated log schemes, because this is not fine saturated just because this monoid isn't finely generated. This fine saturated includes the fact that the monoids are toric and hence finely generated. It turns out that's not such a serious issue. But there are still some annoying things, which is that this property of defining E, so this condition that alpha of S1 is non-zero, that's a condition that can be disturbed under infinitesimal thickenings. Right, so you might have this curve, for example, here, you might have alpha of Sn being 0 for n non-zero, but then you take a little infinitesimal deformation of C, and then suddenly alpha of, say, 1, 1 is now a nilpotent, not 0. And nilpotents are bad too. We can't multiply a nilpotent by something that's not in the ring. And as a result, if you do a little infinitesimal deformation, this monoid changes. And it's not that hard to see with, if you set things up correctly, is that you're going to lose some stuff over here. Eventually you will have everything down here, but you'll just lose some stuff here. And that means that the deformation theory is strange, because the infinitesimal deformations change the combinatorics. And in the previous talks, the combinatorics was always sort of a deformation, infinitesimal invariant. So that causes all sorts of little technical problems. So n bar E bar T is not preserved under infinitesimal deformations. So as a result, so stable maps. So if we have sub C to W to X. So of course, we go through the theory exactly as before. We define a stable map in exactly the same way, except now we allow C to have these additional kinds of points, which are punctured points. But this phenomenon of this monoid changing actually produces a local obstruction to deforming these curves. Because, of course, remember, when you're trying to define this logomorphism, that means in particular you have a map from m bar x to m bar c. If when you deform m bar c gets slightly smaller, you may not have enough room for m bar x anymore. So that creates local obstructions to deformations. And that's awful for deformation theory. Deformation theory requires some local unobstructedness. But there's a solution, which is to work with a relative deformation theory, a relative obstruction theory. So need to work with relative obstruction theory over some kind of Artin stack which encodes this combinatorial obstruction to deforming. then there's a combinatorial obstruction to deform. And this Arden stack need not be equidimensional. So not necessarily pure dimensional. Okay, now if you know anything about how virtual fundamental classes are constructed, this is a problem. Because you no longer know what the virtual dimension of your cycle is supposed to be. So we actually don't have, in general, a virtual fundamental class. Rather, we have some sort of pullback, virtual pullback, where we can pull back classes from this Arden stack to get classes on the moduli space, but we don't know what they mean. That's, sort of, I think, still something that we haven't understood well. But in special cases, you can prove that it's equidimensional. Including the case of interest for us for defining those invariants which define the structure constants for the algebra. So it's a rather delicate machinery to use at the moment. The real reason why we originally, the four of us originally developed puncture invariants is that they're really going to be the key ingredient for a general gluing formula for log Gross-Witten theory. The idea being that if you have some big complicated logarithmic curve, if you just restrict the logarithmic structure to components, or to pieces, you split up the curve into pieces, then the natural gadget you get is a punctured curve. No longer have a logarithmic curve. And then the idea is that we want to go backwards. We want to take punctured curves and start to glue them together to get ordinary log curves. So that's something that's very much in progress. I hope that the first paper of that series will be on the archive next week, but probably depends on how tired Bernd is when he gets back home. Okay, so anyway, that is it sort of in brief. All right, so how does this take care of? I haven't told you how this takes care of negative order decantancy. So the point is that now let's look at the analog of contact order. Contact order at punctures. So, out of puncture, we have this map F bar flat. So if we're given there's C with this puncture P over W mapping to X, then of course we have this map F bar flat from M bar X F of P to map E bar P, where E is this funny sheaf, funny log structure. And this is contained in M bar C P, the original log structure before we put the puncture on, plus the group Z. It's not exactly equal as we saw, say, in that example, but you contain sort of might contain a large piece of this. And then you have the second projection, this time projection to Z. And of course then the composition is the contact order. So this allows then negative, so elements that aren't necessarily just in the dual of this monoid, but actually in the dual of the group. Okay, so let me just do a simple example, and then I'll go back to the del Pesto surface of degree 5 and show you the equations directly. So as a simple example, let's just take X a surface, smooth surface, D, a -1 curve on C, on X, and we're going to take the underlying stable map to be just the identification of C with D. Sort of an isomorphism D. Now, if D had self-intersection 1, then morally you would expect that you can deform a copy of D away and get a curve which is transversal to D meeting at one point. And that would be along the ordinary relative invariant along with the Gross-Hacking-Keel invariant. And you could then have also just use the curve sitting on D, and you would still be able to put a log structure with contact order 1 at some marked point on the curve. So here, the point is that we're able to now put a puncture structure at a point on C, which will absorb the -1 bit of the self-intersection. So we have then C P to X. So this is the puncture. So that's very vague. I'm not telling the details of how this works. But if you understand log structures well enough, you should be able to convince yourself that there is such a log structure. C will be of this sort that I showed you earlier. Before you puncture, you just have an n factor. So here we have nc with OC star plus n. Sorry? If you're used to, I think I understand the question. If you're used to relative invariance, so in relative invariance, if you have a curve falling into a divisor, you have to bubble off the divisor. So you have something like, you'd start with, here's X, here's D, and then what you would do is glue on a P1 bundle over D, the projectivization of the normal bundle. And then, so in ordinary Gross-Hacking-Keel theory, in ordinary relative Gross-Hacking-Keel theory, as Jun Lee defined it, if you had a curve of contact order 1 with D falling into D, you would represent it by having a curve up here in this component with contact order 1 over here. Now, what happens in this case is that really this curve is represented by a curve like that, which has contact order 1 here, but has nothing attached to it on the other side, which isn't allowed in ordinary relative invariant, relative Gross-Hacking-Keel theory. So another way to think about it is that you have a section of the normal bundle that's allowed to have a pole. So I don't know if that helps, but it's a bit abstract. Okay. Yeah, so let me now pass the Del Pesto surface of degree 5 and show you how we get those equations, and then that will be the end of my talk. So let's take X is dp5 with, of course, as before, the boundary given by divisors di. And then we also have, if you recall, the other 5 minus 1 curves. which do something like that. I call those things E1, E2, and so on. So that was the picture from last time. And let's look at theta I times theta I, sorry, theta I minus 1 times theta I plus 1. Okay, so to really do this carefully, you need to look at every possible output point. And so you have to look at every. We have b over here, and you have to look at the possible coefficient for any interval point on b of z. That takes a little bit of work. It's actually not so hard because it's all you can narrow down the possible points very quickly using some intersection theory. Because the curves that you want have to intersect, as we'll see in a second, have to intersect the boundary divisors in very special ways. So let's look, for example, at coefficient of theta 0. So by the way, in this ring, so 0 is the origin here. Theta 0 is always the identity in the algebra. So I could also write that as well. Okay, so what does this mean? So first of all, what's the stratum corresponding to 0? That's the whole space. So here we have r equals 0, and zr is all of x. So we just pick some point z in x. Now, notice here we don't need to talk about negative orders of tangency. If negative 0 is happily positive, or sorry, is happily non-negative, it's saying actually there's no tangency whatsoever with the boundary. We're not interacting with the boundary at all, which is good because you could choose that in the middle of x. So we need curves C meeting di minus 1 and di plus 1 transversely at one point. And passing through the point Z. Okay, so it's maybe not entirely obvious from what I said, but the fact that C has no contact order with, has zero contact order with any other divisor says that we need C, so the class of C, dot all of the dj's should be 0 for j not one of these two. So we're looking for curves which meet di minus 1, di plus 1 at one point with multiplicity 1 and are disjoint from all the other curves, all the other boundary curves. And that actually completely determines the class C. In fact, the only possible class that has this property is C is di plus EI. So in other words, as a class, this is one curve in the classes, well, let's say I equals 2, D2 plus E2. You see it has the right intersection with D1 and D3. It's disjoint from D4 and D5. And the intersection of D2 is 0 because you have -1 from this and 1 from this. So this class does the right thing. And now, in fact, the dimension of the linear system, di plus EI, is 1. Just a little bit of classical algebraic geometry there. It gives you a conic bundle structure, a family of conics on on the Del Paso surface. So of course there's a unique one through any given point. Thus, there exists a unique curve in this linear system passing through Z. And that curve will look something. So Z is somewhere over here. It will be a conic doing that. Okay, so this is really kind of the easy case because it doesn't involve any non-classical logarithmic Gromov-Witten theory. You don't have to worry about the pesky orders of tangency. So what do we learn? Coefficient of beta 0 is, well, we have the number n beta pqr, in this case is just 1. There's one such curve. But remember, we also weight it with the element of the monoid ring, the base, given by the class of the curve, so that's z to the di plus ei. Okay, so that one's easy. It turns out, again, just by looking at intersection numbers like this, and again, in the announcement paper, you can see some slightly simpler example worked out, but the idea is the same. And again, good exercise, check that these are going to be the only two contributions. Coefficient of theta I. Well, in this case, what's the stratum corresponding to the point? So remember, theta I is supposed to be the theta function associated with the primitive generator of the ith ray. So in this case, Zr is just di, that's the stratum corresponding to the ith ray. So you pick some point Z in Zr, in di, and now you want curves transversal to di minus 1, di plus 1, as before, and meeting di, well, and order of tangency with di being minus 1, at the point Z. So in particular, this means that C, the class of C dot di minus 1 is 1, class of C dot di plus 1 is 1, and the class of C dot di, in order to get negative order of tangency, has to be minus 1, just like that example of the minus 1 occurred earlier. Well, there's an obvious choice that does this, which is C is equal to di. So that picture is, again, very simple. The curve in question is, so here's di, and we have this point Z, and there's the curve. It has 3 marked points, one here, which interacts with di plus 1, one here, which interacts with di minus 1, and then the last point where we have negative order of tangency 1, minus 1. Which is fixed to be at the point Z. So again, it's clear there's only one such curve, and now the coefficient is z to the class of the curves, z to the di. So putting this together, we see that theta I minus 1. Well, first you convince yourself there are no other curves contributing. And as I said, it's not really that hard. It really comes from the fact that the intersection numbers, if a curve actually realizes one of these logarithmic punctured curves, its intersection number with the boundary divisors is exactly what you expect it to be given the expected intersection, expected to be given the tangency orders of the marked points. That's why C dot di is -1, because we're expecting -1 order tangency. So putting this together, what we get is theta I minus 1 times theta I plus 1 is z to the di plus ei times theta 0, which, as I said, is the unit in the ring, plus theta to the di, theta I. And if you compare that with the formula I wrote down earlier, you'll see it's the same thing. Okay, so that's it.
I have a question.
Yeah. So actually, let's should we switch to Skype first once we start? But we have a question here too. So, but let's switch to Skype. Okay. So I'll quit this.